Right, hi everyone. So, optimization, this is one of my favorite topics because it really puts puts differentiation on the map. uh, Now, it really gives it a practical purpose. Not that it wasn't practical before, but this is something you can really put your hands on. All right. So, what optimization is just giving you a bunch of scenarios in which you can optimize problems. Now, my professor at university, he was awesome. His job, he got commissioned by Heinz to create kind of the most cost-effective, most efficient shape for the baked beans cans. Actually, made an absolute fortune out of it. And this is big business stuff. Being able to find the least amount of material needed to hold the maximum amount of volume. And this is exactly what optimization is. And it can be really useful just literally in real life problems, really. Let's see how we do it. Go for an example. So it says a rectangular sheet pen is to be made out of 1,000 meters of fencing using a pre-existing straight hedge for one of the sides. So what's that saying? It's saying that there's this hedge, doesn't matter how long it is, right? There's a hedge, and it's saying a rectangular sheet pen is made out of 1,000 meters. So rectangle, I'm going to draw a rectangle to include the hedge, right? And we know that we have 1,000 meters of fencing available, and this hedge already forms part of that rectangle. So actually I only need to worry about 3 sides, okay? So if I say this is side X and this is side Y, let's say, and remember because it's a rectangle they'll be opposite each other and the same length. So this is Y and there's X. We can start to build up our problem because we're saying 1,000 meters must total X plus 2Y, right? There we go. That's a good start. The question's asking us to find the maximum area possible. Okay? So we're trying to find area. So when you get a problem like this, they're telling you what it is they want you to find. So first you need to come up with an expression of what it is I'm trying to find. So this hedge, by the way, would be length X as well, wouldn't it? It would match the opposing side here. The area, this whole bit in the center for the sheep to go in, the area, of course, is X times Y, isn't it? Right? Now it wants us to find the maximum area. You know from the previous video, to find maximums or minimums, well, that's turning points, isn't it? That's turning point. So we need to differentiate. As soon as you hear maximum or minimum, you're thinking turning points. How do I find turning points? Well, I differentiate, yeah? But the problem you have is that we can't just find and this is the point as well. We have a equals x times y. You're so used to having y equals and then going, oh, dy by dx equals, but it doesn't matter. You could have z equals 4t squared, and dz by dt would equal 8t. Can you see? Whatever the variables are, you can just differentiate as normal. If you had f equals 3g squared plus g, df by dg equals 6g plus 1. Do you see? It doesn't matter what the letters are. So the same applies here. Here you've got just capital A. So we need dA by d something, but the problem is, notice on these right-hand sides, you only have one variable, t or g, but here you have 2. So we need to combine it so we have only one variable in here. But we can do that easily, can't we? Because we know that actually x is the same as 1,000 subtract 2y. And that can be substituted into a then. So therefore a is x, which is 1,000 minus 2y times by y. So therefore, expand that out because it's not in the form of ax to the n yet. So 1,000y minus 2y squared. Fantastic. Fantastic. That is your area function. So if we graph that, 1,000y, it doesn't matter what, like, so y equals 1,000, x subtract, it's just for autograph that I'm using y, x's instead of the y's, minus 2x squared. What we got here? Okay, so just like zoom that axis out, you can see here that this is the area function of that rectangle. Yeah? The area function of that rectangle. So here is area, and here is the length of y along here. Obviously, it makes sense. If y's length was 0, so if this length here was 0, gone, you just have a line. So the area would be 0. Do you see? If the length was 500, so if y was 500, then I'd get 500 here, 500 here. That's used up all our fence. So therefore x would be 0. So I just have a line, don't I? And the area of a line is 0. So somewhere in between has a maximum. Can you see? This is a maximum area here. This is the turning point. This is the maximum that we can get. So can you see that all real life problems can be different, can be modeled as a graph? This is why graphs are so important, because when it comes down to it, you can't see crap without a graph. Nothing makes sense without the graph. But now you can clearly see what the maths is trying to do. It's trying to find this maximum point here, the maximum area. Okay. So let's go for it. So we know area is that. We're going to differentiate to find the area with respect to y. There's our variable y, there's a. So that gives me 1,000 minus 4y. We're trying to find the maximum, so this equals 0 at our stationary point, just like before. So now we can solve. So 1,000 minus 4y equals 0. So therefore y equals 1,000 over 4, which is 250. So we know that y is our 250 meters. So the maximum area produced is when y equals 250. And if y is 250, then we know that x is 1,000 minus 2 lots of y. So therefore, x must be 1,000 minus 2 times 250 equals 500 meters. Okay, so there's your dimensions. You know that x equals 500 and y equals 250. Does that make sense on our graph? Yes, it does. There's 500, y is half of that. Boom. There's y equals 250 over there. I know it's a bit confusing with the x and y change, but hopefully that principle is there. Remember, it says find the maximum area though. So we haven't actually found the maximum area. So to find a max, we need to put our y value back into our original. We know this is 1,000 times our y, which was 250, minus 2 lots of 250 squared. So the maximum area possible, 1,000 times 250, subtract 2 times 250 squared, is 125, so 125,000 meters squared. There we go. Answer to the number 1. Number 2, find the dimensions necessary to achieve the maximum area. Well, we did that. X needs to be 100 meters and Y needs to be 250 meters. So you could say 100 by 250 meters are the dimensions. Done. Nice. Love this. Love this topic. It just brings it all together. Here we've got a situation where we've got a matchbox, and this is a cross section of a matchbox. So if you turn a matchbox on its side and looked at it cross section on, you can see that the cardboard was folded in this fashion and then glued on top. So we'll assume that BA and FE are the same distance. Obviously they're going to be slightly off in real life, but in this modeling assumption, who cares? We're talking like fractions of a millimeter, really. Now it says the total length of edge, A, B, C, D, E, F, so i.e. the total edge of cardboard which is folded is 12 centimeters. Calculate the length of AB and BC, which will give the maximum possible cross-sectional area. So we need to think about this. All you do is you take your picture and you start labeling stuff up. So if that one's X, this one must be X, but so must that one, right? Because we're folding the lip on top. So you've got to account for that lip. And as it's a rectangle, we're going to have sides Y, let's say. So we know the total length of the edge is 12. So 12 must be the same as X plus X plus X, so 3X plus 2Y, right? And then again, we look at what it wants. It wants maximum area. So straight away, area, well, the area of that rectangle is still X times Y, isn't it? That's the area. We want to find the maximum, so straight away we're thinking differentiate, set equal to 0, put the point in. But we can't because this is not in the form of one variable only. So we need to rearrange this one. So we get 12 minus 3x equals 2y, so therefore y is 6 minus 3 over 2x. You see, divide everything by 2, and now that can be put into here. So a equals x dots of y, which is this. Can't differentiate yet because it's not in ax to the n form. So there we go, sorted. And now we can differentiate. And now this, remember, corresponds to an area function. Just make that clear again. So file 2D, what we got? Y equals 6x, subtract 1.5 x squared. There we go. So we make our y a bit bigger. There we go. Same again. So quadratic on its side. Here's the maximum point. Here's the turning point. Here's where the area, over dx equals 0. And this is what we're trying to find. All right. So let's go for it. Go over here then. So dA over dx equals differentiate 6 minus the 2 comes down. That's 3x, isn't it? 3 over 2 times 2 just gives you 3 equals 0 at stationary point. Really important to add that. Let's find x then. So x must be, move the 3x over, divide by 3, 2. Yeah? But remember, it wants the maximum cross-sectional area. So A max must equal, and we can whack our 2 in there. So 6 times 2 minus 3 over 2 times 2 squared. That's 12 minus 6. So 6 centimeters squared is our maximum area. And if it wants the dimensions, might as well with x equals 2 centimeters and y then equals, from here, 6 minus 3x over 2. So 2 over 2, that's 1. So 6 minus 3, y must equal 3. And there we go. Centimeters. Fantastic. Let's go for a formal example then. So this one looks much more meaty, but it's the same principle. So this one says a solid glass cylinder used as an expensive laser amplifier has volume 75 pi. So you know you've been given, like before, the volume, and you know you're going to have to use that. The cost of polishing the surface area of this is £2 per centimeter squared for the curved surface and 3 pound for the cylinder, the circular top and base. Given that the radius is r, show that the cost of this is this. Okay, so let's think about this. First, we'll draw a picture. It always helps drawing a picture. So there's a cylinder. We know that the radius is r, so here's r. We know that the volume is 75 pi, right? So here we've got r, and we'll give it a height h. Okay. So we know the volume is 75 pi. We know the surface area, and we can come up with expressions for that. So let's do it. The volume for this thing is pi r squared. That's the area of that circle. And then it's times by h, isn't it? So it comes down here. That's h. So there's the height. And we know this thing is 75 pi. That's helpful. We're trying to find the cost of polishing. Well, really we're trying to find then the cost of polishing is given by the surface area, isn't it? Because it's £2 for the cylinder and it's £3 for the circular top. So let's go for that. So we know that the surface area of the cylinder bit, so we'll call that bit the what do we call it, of the glass cylinder, so I don't know, SC. The area of that is going to be the circumference, so 2 pi r all times h, isn't it? So the circumference, and then it's dragged down by h, and then you can flatten it out, can you? So there we go. And we know the surface area of the tops, let's say st, that thing is just going to be pi r squared, but there's two of them, aren't there? There are two bases, so 2 pi r squared. And now we can put this stuff together. So the total cost equals the cost of the cylinder and the cost of the tops. So this is 2 pi rh plus 2 pi r squared. And remember, the cost is £2 each for the curved surface area. So we should charge our curved surface area by 2, and we should charge the top by 3. So this is 2 lots of that and 3 lots of that. That's your total cost, isn't it? Okay. So this is 4 pi rh plus 6 pi r squared. Now look at the question. It's saying show that the cost is this, and this doesn't have any h's in it, does it? And that's where this equation comes in. Because you know that pi r squared, h is 75 pi, you can come up with an expression for h, can't you? So h must be 75 pi divided by pi r squared, which gives you the pi cancels 75 over r squared. That's helpful. And now we can whack that into our h here. So this is 4 pi r, where h is 75 over r squared, plus 6 pi r squared. We're happy with the 6 pi r squared. We've got that. And now we've got this last bit. So we're going to have our r and r cancelling out here. So 4 times 75 is 300. We got our pi r plus 6 pi r squared as required. So as required. There we go. That's what it asked us to find, and we found it. Fantastic. So that was part A. Part B, use calculus to find the minimum cost of the polishing given your answer to the nearest pound. So again, if we drew this as a graph, so just really trying to emphasize that all this stuff is linked to graphs and finding stationary points in graphs. So this is 600, where we go? Oh, so 300 pi 300 pi over r, so 300 pi divided by x, and then we got plus 6 pi x squared, bang, and here's your graph. So we're trying to find the lowest point of this graph, and if we carried on, if we made our axes a bit bigger, let's start this, right, it really makes it obvious, doesn't it? The lowest point, so if this is cost on the y-axis, and this is the radius of that cylinder on the x-axis, the minimum is clearly here. This is the lowest point. This is where we have a turning point where our dc over dr is going to be 0, and this is our minimum, isn't it? So let's do that. Let's go for it as we were before. So part B, got it all in terms of one variable? Fantastic. But at the moment it is not in the form of ax to the n. So this is 300 pi r to the minus 1 plus 6 pi r squared. Now we can differentiate it. So dc over dr equals minus, the power comes down, 300 pi r, take 1 from the power, plus 12 pi r equals 0 at stationary point. So this is the same as minus 300 pi over r squared equals minus 12 pi r. You see how important it is being able to manipulate your indices? I've just moved it all over. The minuses can all cancel, right? You can times up by the r squared, so I get r cubed equals 300 pi over 12 pi. You see, so I've moved that up there and I've divided by 12 pi here. The pi's cancel. 300 over 12 is 25, and so r is the cube root of 25. There we go. So find the minimum cost, given your answer to the nearest pound. So cost minimum equals 300 pi over our cube root 25, putting it into here, plus 6 pi cube root over cube root 25 all squared. So our cost minimum 300, so cube root 25, using that answer button trick, 300 pi divided by our answer plus 6 pi answer squared is 483 pound 48, which is 483 pound to nearest pound. There we go. Answered. Finished. Now, part C says justify that your answer contained as a minimum. Well, we know how to do that now, don't we? Because if we want to classify our point, that means classify, we could just differentiate again. So you know that dc over dr is minus 300 pi r to the minus 2 plus 12 pi r. Differentiate again, d squared c over dr squared is minus 2 comes down, so that's 600 pi r to the minus 3 plus 12 pi, which is 600 pi over r cubed plus 12 pi. If you whack in r equals cube root of 25, your d squared c over dr squared will be positive, and therefore this is a min as required. Okay, there you go. All done. That's optimization in a nutshell.